All right, welcome back. We're talking about the factors that increase the rate of a reaction. And we're on our fourth factor, and this one is surface area. Now, we talked briefly about this when we talked about the rate at which substances dissolve, and the argument's very similar. If you put in a cube of sugar and granulated sugar in equal masses, the granulated is going to dissolve faster. And there's a similar process going on here. And it's because an increase in the surface area, now that means you've crushed it into smaller pieces. Like granulated sugar will dissolve faster. And what happens is when it's in a big cube or a big piece, only that amount of area is exposed for attack for the reaction. But if, on the other hand, you break up the surface area, you not only have those areas, but the reactant has a chance to get in between. The other reactant does. So you expose more surface of the solid for attack, and it can get down inside there. So it increases the opportunity for effective collisions. So you increase the frequency and you increase the rate of the reaction by doing that. So an increase in surface area means there will be more collisions. So increase in frequency, another way to say that, increase in frequency or more collisions. Not only that, but this can actually improve orientation as well. Not always, it depends on the reaction, but there can be an improved orientation effect there. So improved frequency or more collisions, and therefore your reaction rate will increase. The next factor, adding a catalyst. And I will definitely do a demo on this in class. It's a very fun demo, and I've got to remember to buy those gummy bears to do that demo as well. Catalyst is a special substance. You may have heard the words like catalytic converter. There's even a song. I remember I was trying to think of who it was. Like Dido, I think. Probably that's old lady music, but that's called catalyst. And what a surface catalyst does, it's a substance that decreases the activation energy. Remember here we have that activated complex up at the top. So that's our activated complex. What it does is it provides an alternative pathway. So it means more molecules. So we have an alternative pathway. And it either makes a new activated complex, so we have a new one, or a more stable. So it's either new or more stable. Lower potential energy means more stable substance. So it's either new or it's more stable. So it decreases the activation energy. Notice that the potential energy of the reactants is the same. The potential energy of the products is the same. Our delta H is the same. Here's what changes. My activated complex energy is lower, and therefore my activation energy is lower. And that's true for both the forward direction and the reverse direction. The activated complex is lower, so the activation energy is lower in both directions. Smaller hill means more molecules have enough energy to make an effective collision. So more particles will have enough energy. I'm going to rewrite that. I don't like the way it's worded. To overcome this lower activation energy barrier. Let's call it that, activation energy barrier. So the rate of the reaction will increase. So you can kind of think of a catalyst as a matchmaker. It's going to bring A and B together. So you get this catalyst in the middle that says, hey, A, you'll really like B. Let me bring you together. Let's meet so you can get to know each other. Okay? So, a catalyst, and these are some important considerations, a catalyst is not considered a reactant or a product. It is not consumed in the reaction at all. It may change a little bit in the middle, but how it starts out at the beginning is exactly how it forms at the end. And then it can go on to react again. Just like a matchmaker can bring two together, gets real involved in the process for a while, but then eventually is freed up. There the match is made, and the matchmaker can go on to make another match. So it's not consumed. And so we don't put it on this side. It'd be kind of awkward. It's kind of like algebra. Things that show up on both sides are canceled. So instead we put the catalyst above the arrow. So for example, MnO2 is a common catalyst. So we would write MnO2 above the arrow. Now, these steps down here, just to introduce some terminology that we'll see again in AP, when we have the steps of an overall reaction, I'm going to add those up here. And if they show up, if a substance shows up on both sides of the arrows, it cancels. So there's X as a reactant and X as a product, it cancels. AX is a product and then it's consumed. And if we bring down just what remains, we get our overall reaction back. So this is the overall reaction, and this is called a mechanism. It's the step-by-step description of what is happening. Now, just a couple more terms here, and then we'll let it go. We have two types of catalyst. We have a homogeneous catalyst, and that's a catalyst that is in the same phase. So if it's a gas phase reaction, the catalyst is a gas. If it's a liquid phase or aqueous, then the catalyst is also aqueous. And we have heterogeneous. If you know what a catalytic converter is in a car, it's a heterogeneous catalyst. In that case, we have a gas phase reactance, and the catalyst is a solid. Okay, so that's just some of the terminology. All right, in our next video, we will begin. This will probably take us 2 or 3 videos to finish up, talking about the 6th factor, concentration. So until then, this is signing off.